We are now talking about normalizing activations with layer normalization. So in the grand scheme of things, what we've done before is we introduced this GPT model architecture where we had several ingredients. One was the embedding layers that we introduced in chapter 2. We had the masked multi-head attention module, which we talked about in chapter 3. And now there are several other things. So we had this dummy GPT placeholder for now, where we said we are going to fill in the blanks in the upcoming sections. And that is what we are going to do now for one of these ingredients, and that is the LayerNorm. So LayerNorm is short for layer normalization. It's a concept that was introduced back in 2016. It's a classic deep learning concept, and it's about normalizing the outputs of a given layer that go into the next layer so that it has a nice property for optimization. And to make this a bit more clear, I think let's take a look at the code examples I've prepared. So I think this will show you exactly what's going on there. And so for the code examples, I'm trying to keep it a bit more conceptual, simple. So we will be using layer normalization in the context of the real LLM. Just for simplicity though, in this video, I want to use a smaller example. So for that, I'm just setting a random seed and then I'm making a smaller example here. Let's use torch.randn, which will generate a random sample of 2 by 5 here, just to keep it small. So just looking at this, it will be 2 samples here. And each sample has 5 dimensions. So we have a 5-dimensional input example, similar to what we have done before in previous chapters. For example, in chapter 2, we talked about a token that was embedded in a 3-dimensional space. Similarly here, just think of it as a token embedded in a 5-dimensional space, just to have some more numbers here. Again, like in reality, we talked about this earlier, the embedding dimensions might be bigger in real LLM cases. So here 768. Here for simplicity, just let's work with a smaller example so that we can fit it on a figure. Actually, I should have a nice figure here somewhere. So what's happening essentially is that we have these 5 input values now for a given example. And now what we're trying to do is we are trying to put them through a small neural network, for example, this one here. And then we get output values, and we want to make sure that these output values are in a certain value range. And so in this case, if we just apply the neural network layer, what we might get is a mean, an average of 0.13 across these values, and a variance of 0.39, which is actually not too bad. So this might actually be just fine. But if you are familiar with classic deep neural networks, there might be problems like vanishing gradient problems and exploding gradient problems, and normalizing the inputs to a given layer and then essentially also the inputs to the next layer helps with stabilizing the training. So the outputs of a given layer, like those, they would go into the next layer in a deep neural network because we have many layers in a network. And if we have, let's say, very small values or very large values, that might be not optimal. It might lead to unstable training. So what we are trying to accomplish here is we're trying to add a certain layer called layer normalization to normalize these outputs that go into the next layer such that they have mean 0 and variance 1. That is our goal here. So let's consider our inputs here, and then let's also implement a small layer like I've showed you before in the figure. So let's use sequential here, and then let's do linear, which creates the neural network layer. And we have 1, 2, 3, 4, 5. We have 5 dimensions, so the input is 5, and the output, let's use 6 to match what we have shown here. So we have this layer here, and then let's actually apply this layer to the batch example. Maybe one more thing we could do technically, is adding a nonlinearity. So nonlinearity could be relu, for example. It's a nonlinear activation function. And yeah, that is, if you have worked with deep neural networks before, usually we pair a linear layer with a non-linear activation function, because otherwise, if we only have linear layers in a neural network, the sum or the combination of linear layers would be a linear function, and that would not be a very useful neural network. So usually we would add nonlinearity so that the network can learn more complex things. So let's do this and look at the output here. So what we can see here is, we get some output values, 2 examples. So the first one corresponds to this example, and this one corresponds to this example, transformed now through this mini neural network. So the first row here is really what we are seeing. If we focus on one example, what we are seeing here. And so before we start with any layer normalization or normalization in general, let's just take a look at the mean and the variance of this. So we could, for example, call mean here. And if I call just mean like that, we'll see what happens is not what we expect, or it depends on how what you expect, but here it's not what we want. So here we get one value, and this is the average or the mean of this whole thing. But we want actually the mean across this first example. So there are multiple ways we can compute the mean. We can compute this mean of this whole thing, but this would be mixing multiple examples, and this is not what we want. The other one we could do is we can do dim 0 here. And so here, what this one will be is the mean across each of those. So if you consider the mean, this and this would correspond to this one, this and this correspond to this one, and so forth. And that's also not what we want, because we're again mixing different samples. And there's actually a different normalization scheme called batch normalization. That's what batch normalization does, if you're familiar with classic deep learning. But batch normalization is actually not really recommended for LLMs, because the way when we train neural networks, large neural networks, and we want to split them across multiple GPUs, for example, one way would be splitting the samples across multiple GPUs, and then we would end up with small samples per each GPU, and that is not very good for batch normalization, which is very unstable then, and so forth. So that is why, long story short, we're using this concept called layer normalization, where layer normalization is independent of the sample size. It's normalizing across this dimension here. So in order to get this dimension, we use the column dimension 1. So this will be then normalizing here, or not normalizing, but computing the mean here. So this one, this value is the mean of the first sample across the features, the feature dimension. I could, by the way, also type -1 here. So to explain a bit more, what we have here is shape 2 by 6. So if I type 0, it will be normalized or computing the mean across this first dimension, 0. But this is the rows, right? So for each, we would normalize that or compute the mean like that. But what we want is we want the mean across the column dimension, like basically going over the columns here. So for that, we go to the second dimension, so 0, 1, and put a 1 here. Oops. And so this is what we are doing. And by the way, we could also write -1, which would be more general. So for example, if I had an extra dimension here for some reason, this one would still give me the same results, right? But if I write 1, now this would give me the, again, mean across this dimension, 0, 1, which is not what we want, right? So this, just to show you, will be slightly different. What we want is we want the mean across here, the feature dimension. Assuming the feature dimension is always the last dimension, we can just use the more general -1 here. So let me just get rid of this again to make this a bit simpler. Now, one more thing is it's still a bit harder to read here. So we have these 2 values, and one corresponds to the first one and one to the second row. We can actually keep the original dimensions. We can do keep them equals true here. And then this one will keep the dimensions. You can see it's these 2. So the 2 dimensions, the 2 rows, it will keep those, which is a bit nicer. So this would be the mean. Let's just call that mean. And we can do the same for the variance here. Let's do this. Okay, so again, we can see what we want is a variance of 1 for nice properties, but we have a different variance. So our goal here is to normalize the data such that this will be the mean of 1s and the variance of 0s. So that's basically what we are trying to accomplish here. And so one way we can accomplish this is by, well, just step by step, by centering around the mean. So if we have an output and we subtract the mean, this will give us the output centered at the mean. So for example, just a simple example, if you consider those consisting of just the value 5, 5, 5, 5, 5, 5, 5, 5, 5. If I subtract the average, which would be in this case 5, 5 minus 5 is 0, right? So doing this should give me 0, right? So here what we get is this. Actually, you can see it's very close to 0. It's not exactly 0. So this is a scientific notation in PyTorch. So this would mean basically 0.9 leading zeros and then 7, 4, 5. Actually, to make this a bit nicer, we can set the print options, and then there should be a psi mode. We can set that to false. And then it will look hopefully a bit nicer. Yeah, so you can see it's basically 0 and 0. So that is what we've done here, just to also make this a bit nicer again. Okay, and now this is how we center at 0. The other one that we do, or what we want to do, is we want to also give it a variance of 1. So for that, we divide by the standard deviation. So the standard deviation is the square root of the variance. Actually, yeah, I could go into more detail here why standard deviation, but that would be a whole lecture by itself. I used to be a statistics professor teaching these things, but to keep things simple, maybe just assume this is the formula for normalization, subtracting the mean and dividing by the standard deviation. And then, so this one should be, let's just call that normed. And this one should still be mean 0. And now, in addition to that, we should also have, we can just do it here, a variance of 1. So that's what we see here. So far, so good. So we accomplished that. That is one part of layer normalization. There's a bit more to layer normalization. It's actually a neural network layer that learns parameters. So let me just copy in here the LayerNorm class I implemented from scratch, and to show you a bit more what I mean by that. So what we see here is a neural network class, and we have an initialization here, like the constructor method, and there are a couple of things. So one thing here is that we have parameters, and as you maybe remember from chapter 3, parameters are trainable neural network weights. So here we have the same size as the embedding dimension. In our case, if we consider this one, this should be a 6. So we have six values here. And the parameter will be making those 6 values trainable. And we call that the scaling parameter. Similarly, we have a shift parameter, and this is zeros. I will get in a moment why it's ones and zeros. So, and then maybe for now, ignore the apps. So for now, what we have here is exactly what we had before. So what we had before, let me also just comment this out and get back to that later, the unbiased here. So what we had before is the normalization. We computed the mean and the variance, and then we subtracted the mean and divided by the standard deviation. This is exactly, so if I write it like this is exactly what we had before, the normalization here. Now we are adding one more concept, and that is this EPS. So what is the EPS doing? So this is preventing a division by 0 error. So if we have square root of 0, basically 0, and we prevent basically dividing by 0. So we add a small value here. It's just like a small placeholder value. So that's 0.00001. So I could also just write it like this. And yeah, so that's what we are doing here. So far, so good. So we have those things, and there's something new now, and there's the scale and the shift here. So to explain what happens, let's maybe tackle it like this. So we have, let's just ignore this for the moment. So what let's do it like this. So because the division comes before. Sorry, not correctly. So let's do it like this. It's maybe easier. So what we're doing here is we are subtracting the mean, right? And so here we optionally add some value back. So we subtract the value, and then we add some value back. And if we check the original value of shift, that's zeros. So we are essentially adding 0 to it, which is similar to not adding anything here, right? So this doesn't have any effect out of the box because it's zeros. However, the network during the training later in chapter 5, it might learn certain values that are more beneficial for the normalization. So it might, but it could technically, what it might learn is to just undo the mean centering. So if the network finds, well, subtracting the mean is actually not good here, it's not helping me learn, I can just learn shift to be similar to the mean, and then I'm undoing this subtraction, right? So what I mean is if I subtract the values 5, and the network learns the shift to be 5, I'm adding back 5, then it's if nothing has happened here. So in that case, it gives the network the option to undo this normalization, long story short. And then similarly, we can do the same thing here for this division by the standard deviation. So here the scale, it's not multiplying the value, right? And so by default, this is a 1. So by default, we are multiplying it by a 1, which doesn't do anything. It's the same as just keeping this value like here, like this, right? However, the network, again, it's a parameter. It might learn different values. It might learn this value here instead of scale, and then it will undo this division, basically, right? So it's just giving the option for the network to learn certain values, to transform the values slightly differently. And this is essentially how a LayerNorm looks like. And by default, it will be the same as our normalization due to the fact how these ones and zeros are set here. Now, let's actually try this in practice. Let's see how it works. Let's do LayerNorm. And then we have embedding dimension character, or value attribute. Argument, sorry, function method argument. And so we have this, and then we apply it to our, let's do the output here. And these are our transformed values. Let's actually double check. Let's just call them temp, or like just outputs normed, something like that. Okay, and let's just see how they look like again. And now let's double check if they are indeed having the properties that we desired. So that would be mean of 1, mean 0 and standard deviation and variance of 1. Dim -1, I think. Keep dim true. Okay, and let's double check. So we can see indeed mean 0 and standard deviation of hopefully 1. Close to 1, yeah. So basically 1 minus rounding errors. The one thing I commented out here is this unbiased. So this is just like a minor detail. So there's if you're familiar with statistics, population statistics and sample statistics, there's a concept like a Bessel's correction term when you compute the variance or standard deviation that you divide, instead of divide by n, the sample size, you divide by n minus 1. So unbiased is basically, unbiased true would be the population statistic, and unbiased false would be the sample statistics. So this would be a whole, again, lecture by itself. I used to be a statistics professor and was teaching these things, but I don't want to turn this into a statistics lecture here. But what we have here is we could technically, let's see if that works, set this to false. You can see the values are slightly different. And that is because we have a very small sample size. So here, if I increase this sample size, make it really large, let's say, it should be then also very large. Oh, I should also make this actually large. Okay, like this. Oh, this is very slow now. Shouldn't have done that. But you should technically see, can I interrupt this? No, not responding. Made it maybe too large. Apologies. I hope it doesn't crash the recording. But in any case, if you make this really large, you should see this should be 1 basically. So this should not, this is only making a difference if you have very small values. And in neural network training, as I mentioned before, we have an embedding dimension of 768. So it shouldn't really make a difference at all whether we use 1 or not. Oh, it actually worked. Let's just maybe try again. Yeah. Okay. Yeah, you can see here it's now almost 1. So the bigger the input is, the less of a difference this correction term makes. And it's really just an implementation detail. It does not matter at all for regular embedding sizes. The reason why I'm setting this explicitly here is that's what the TensorFlow or PyTorch, sorry, what the GPT team did when they used TensorFlow to train GPT. And here we are re-implementing things in PyTorch, and PyTorch has different default values than TensorFlow. So that's why I'm just setting this to mimic the same behavior that the original OpenAI GPT team did used when they were training the model. Long story short, if this was all a bit confusing with this unbiased setting, it's just an implementation detail. I would not worry about it too much. It's not that important. The main message here is that we are normalizing values so that they have mean 0 and variance 1, which will give the network nicer properties, the values nicer properties during the optimization. And this is one building block, the normalization layer in the transformer network, the GPT network here, the LLM. So we are using it in several places. We used it in this place, the final norm here. And we are also going to use it in the transformer block when we are implementing the transformer block later. Anyways, I hope this was useful and explained a bit what layer normalization is. And in the next video, we will tackle some of the other placeholders.
Get this book at manning.com.